Okay, so that's the review. That's the quick review of what we did last time. Are there any questions about that?
No, sir.
Okay, so if you remember what Riaz was doing, his problem is how do I solve this this nonlinear heat equation, basically the Black-Scholes equation. And what he does is it's basically at each time step you evolve the system. And to evolve the system at each time step, you need to solve a boundary value problem at each step. So I thought that this time I would do something that's a little bit simpler and just discuss how you would use Python to solve just the boundary value problem part. I'm not going to march anything through in time. I'm just going to discuss how to solve a boundary value problem. Okay. So let's just look through this simple ODE we've seen before. Y prime of x equals y of x. And let's say that there's going to be 5 equally spaced nodes on the interval from 0 to 1. Okay. So then the spacing is 1 over 5 minus 1, 1 over 4 at 0.25. And then the points that you pick on the interval will be 0, 0.25, 0.5, 0.75, and 1.0. Okay. And now we label the unknowns. So u is the approximation to this function y, and u sub I means this is my numerical approximation to the function y at the point x sub I on the unit interval. So you have unknowns, u0, u1, u2, u3, u4. And we would ask, what's the derivative at x0, which is equal to 0? So what's the derivative of y is what we would like. Well, then we'd say, well, okay, what's the derivative then of u, this approximation? Well, we need the approximations of those. So the forward difference estimate would be u1 minus u0 over delta. We can't do a backward approximation at the initial point of the interval because there's no point behind it. That would take us outside of the interval. Okay, so is that okay?
Yes, sir.
Okay, now now the question is, let's go back here and say if I'm using forward difference to estimate derivatives of these yi's, then the question is, how do I approximate the actual value of the function? Okay, so there could be different ways of doing it. All right, so one way of doing it would be to say 1 over delta minus u0 plus u1. That's the forward difference estimate at u0. And then I could say that's supposed to be equal to u0. Another way of looking at it would be to say that I'm going to think of this as the approximation of the derivative across the entire subinterval from the point x0 to x1. And then I want an approximation for the function value from x0 to x1. So one way of doing that is to take 1/2 u0 plus u1. Okay, so is it okay, this right-hand side, 1/2 u0 plus u1? I mean, it would be perfectly fine to take u0 as the estimate if you wanted to, but I mean, there are different ways of doing this. So this is the way we do it. For this problem, I've decided that's the way I'm going to do it. Okay, so now that this was the estimate. This is the numerical way, or a numerical way of writing down approximations to that original differential equation at the point, you can think of it either as occurring at the point x0 or on the interval from x0 to x1. So now, if we do the same thing for at all the other nodes, we're using a forward difference estimate, right? So we're going to use the same kind of estimate at each node. Then what you get is this, the pattern stays the same, and you get these four equations, all right? As you go from node xi to xi plus 1, all the indices that you have, all these subscripts that you have, they increase by 1. Okay? So now you have these four equations. Okay. Now, we need to solve for U0 through to U4. And let's say that I want to solve for U1 in terms of U0. So if I take this first equation here, and then I rewrite it, I get this equation. I bring the U1 term over to the left, and I bring everything involving U0 over to the right. And then I solve for U1, okay? So I get some coefficient times U0. And let me call that coefficient alpha, okay? So that I get U1 is equal to alpha times U0, where alpha is 1 over delta plus a half and 1 over delta minus a half, okay? So that puts means that method of solving for U0 for U1 in terms of U0, I can use it to solve for U2 in terms of U1, right? Because the equation is the same except all the indices have increased by 1, right? So now I get also that U2 is equal to alpha U1, but U1 was alpha U0, right? So that's U2 equals alpha squared U0. Similarly, U3 is equal to alpha cubed U0. And U4 is equal to alpha to the fourth U0. Okay, we didn't specify an initial condition, so you could have any value of U0. Now let me fix that. You could have had any value for U0. So is that okay? So in this simple case, the equation is actually simple enough that we don't really have to compute much of anything, right? So we've solved for all the UIs in terms of U0. U0 was not specified by an initial condition, so any value of U0 will work. Okay, so this one all right?
Yes, sir.
Okay, so now I did that for 5 nodes, but I could do it for n nodes also, right? So what really changes is that delta is equal to 1 over n minus 1. Last time n was 5, but let's just call that n. Okay, you set up your xk is k plus, sorry, that's not L. That's k plus delta. Okay. And now if I want to, I solve everything the same way. I can solve for U1 in terms of U0, U2 in terms of U1, and so on and so forth. The same pattern emerges. And I get, I get this as a result, right? UK is equal to alpha to the k U0. Alpha is the same as before. Okay, it follows the same way. Okay, now if we want to do the initial value problem, let's say we set U0 equal to 1. Okay, so then all these U0s in this column of equations All those u zeros are equal to 1. And then I get uk equals alpha to the k. All right. So I don't really have to do much computation here at all. Okay. But okay, if that's okay, shall we go on to a slightly more sophisticated way of looking at it? All right. So now what if we said you use forward differences in that, and that's not right. If you can use central differences, which reduce the error markedly, then why didn't you do that? All right. So let's look at this in terms of central differences. You have y prime of y equals y of 0 is equal to 1. Let's set the value at the first node to be u0. And then, okay, so from the initial conditions, u0 is equal to 1. We don't have to solve for u0. For the interior nodes, what's the central difference formula? It's uk plus 1 minus uk sub minus 1 over twice delta is equal to, sorry, that shouldn't be u2. That should be uk. Is equal to uk. And then for the last node, you have to decide what to do. Now, un minus 1 is going to appear in the central difference formula for the derivative at un. So you could perhaps not have that as an equation. Or let's decide if we want to put an equation in, maybe we'll use the backward difference formula for the last node. Okay. So for 5 nodes, what does this look like? The first one, u0 is specified. So this equation says, this matrix equation says that 1 times u0 is equal to 1. Okay. And then the central difference, we have the central difference formula for the derivative at u1. We have the central difference for u2. We have the central difference for the derivative at u3. And we have the backward difference at u4. Okay. So for the other formulas, I've pulled everything over to the left-hand side. So the left-hand side of the equation is equal to 0. Okay, so this is what the system looks like for 5 nodes, written as a matrix vector equation. Okay. So what do you notice? What's the first thing that strikes you about the form of this big matrix on the left? What name did we give to these kinds of systems before?
A diagonal matrix?
Yeah, it's a tridiagonal matrix, right? And it's a very regular tridiagonal matrix, right? It's mostly the same terms occurring throughout. Okay, so once again, it is a very grave sin to do general matrix inverses. If you have a tridiagonal system, use the specialized solvers for tridiagonal systems. And I showed you I showed you code before for how to do it, and then I also suggested that you write the code once for yourself just to see how it works, but then you should use the what's available in the various packages and libraries, right? So that's what we're going to do here. Okay, so the system is tridiagonal. We discussed Thomas algorithm before for doing this, and we had the code for the Thomas algorithm. But Python has a method for every common situation in linear algebra. So I'm gonna take a brief detour through that, and then I will get back to this. I'll get back to the problem that we were doing. Okay, so there's there's a module called scipy.sparse. Okay. And we're going to use that. Okay. So the first thing you want to do, so you import numpy as np, because we're going to use numpy arrays to this problem. The method that we're going to call from the sparse module requires these numpy arrays as inputs. Okay, and we're going to import the sparse module. So import scipy.sparse as sp. Okay, so we want to solve ax equals b. So let me give you a problem to be solved using this sparse library as sparse methods. Okay, so let's suppose we want to solve ax equals b. A is this tridiagonal matrix, and b is this column vector. Okay, so you've got three diagonals. So you've got this diagonal where you have you have a lower diagonal, -1, -1, and -1. And then you have a main diagonal, 1, 1, 1, 1. And then you have an upper diagonal, -2, -2, -2. So what you're going to do is you're going to specify that I am storing a matrix which has these three diagonals. Okay, and I have a right-hand vector, this b, which is this column vector, b equals 1, 2, 3, 4. Okay, so this is the way we do it. Okay, so once again, you have a lower diagonal of -1, -1, -1. You have a main diagonal of 4 1s, and you have a lower diagonal of -2, -2, -2. Okay, and notice that your main diagonal has one more entry than the lower diagonal and the upper diagonal. Okay, so you might want to be a little bit careful with that. So I store this lower diagonal of 3 -1s as a numpy array. Okay. Then I store the upper diagonal as a numpy array, and I store the lower diagonal as a numpy array. I'm not going to bother to store all those zeros. I'm just going to store the three diagonals, which are going to define that matrix A. Okay, so now what we do is we use scipy.sparse.diags to construct a sparse matrix. So this diags knows that you're going to feed me a list of three arrays. Sorry, a list of three arrays, which are the diagonal entries. And then you're going to tell me where those diagonals live within the matrix A. So when you specify -1, that means that the first entry here, diag 1, is the lower matrix, is the lower diagonal. When you specify 0 here, that means that diag 2 is on the main diagonal. And when you store 1, that means that diag 3 is the upper diagonal. Okay, so up to here for the construction of A, is that clear so far?
Yes, sir.
Okay, now there's an optional input, which is called the format. So there are different ways of how you store this. And there are different formats for storing these matrices. And if you leave it out, it'll decide, it has some default as to how it will store it. Okay. But sometimes the methods that you're going to apply to this sparse matrix, those require that the sparse matrix be in a particular format. Okay. So in this case, if I didn't specify a format, it would, the method that I'm going to use later on this A would fail. Okay. So for that reason, I've picked a common format, which is CSR. Okay. All right. Now, if I want to see what the matrix A looks like in sort of the standard dense format, there's a command toDense, right? So I can say A to dense, and I can take a look at it, and I can be satisfied, at least for a small system, that it seems to be correct. Okay. So that looks okay. Now, there's a solver for sparse matrices, and it likes to have the sparse matrix in a particular format. So that's the reason I've used CSR as the format for storing it. Okay, so we want to solve, we tell it what B is. That was the column vector 1, 2, 3, 4. And now what we're going to do is we're going to import scipy.sparse.linalg. So that contains the solvers for doing linear algebra problems. Okay, so the result is given by scipy.sparse.linalg. Use the method spsolve. So it's a sparse solver for the system AX equals B. Specify A and B. All right, so we give it A and we give it B. And then we give it the result, and we print the result. And if we take A times the result and minus B, we get the zero vector as we should. Okay, so that's how we go about solving. That's how we go about solving these sparse systems. Okay. All right, so now let's say I go back to the initial value problem as before, and we'll have n nodes. We'll make it a real large number of nodes. And then I construct the lower diagonal, and the lower diagonal had entries that look like -1/2 delta. Okay, except for the last one that looked like -1 delta. Okay. The main diagonal, it had entries which were all -1, except for the first entry, which was 1. Right, that was the one that specified the initial condition. And the last entry is 1/delta. And the third diagonal, it had entries that looked like 1/2 delta, except that the first entry was 0. So now, once again, to specify a diagonal, a tridiagonal matrix, give diags the 3 diagonals, tell them how they're offset from the main diagonal, and give it one of the acceptable formats. Okay, we don't want to use toDense to check, because right now it's just too big for us. Okay, and in the right-hand side was all zeros except for the first term, which was 1. Now we use spsolve to solve AX equals B, give it AX and B. Okay, so we have a very long result of n entries, and the last entry should be the exponential of 1. Okay, and it differs in the 4th decimal place. Okay. The last 2 entries are in fact the same, and that's because we've switched from a central difference scheme to a lower order approximation of the derivative. So probably that last equation was not needed in this case. Okay, there are other solvers that you could use. You could use a conjugate gradient solver if you wanted to, for example. Okay, so now do another problem. And as I said, with the problem that Riaz was doing, you're solving a boundary value problem at each step. So I thought it would be good if I just showed you, without the complication of going forward in time, I would just show you how to solve the boundary value problem once. Okay. So with the boundary value problem, you have an interval a to b, and you have a differential equation on it, and you could specify conditions on the boundaries. So one would be to specify the values of the function on the endpoints of the interval. The other would be to specify the derivatives at the ends of the interval. Or you could have some mix of derivative and function value conditions. Okay, so how about this one? The problem is y double prime of x equals minus 4 pi squared sine of 2 pi x plus 1. Y of 0 equals 0, y of 1 equals 1/2. Can you tell me what you think what would be the form of the solution? What kind of function, if I took its derivative twice, would be give me something like a constant times sine 2 pi x plus a constant? Okay, let me ask an easier question. What is the derivative of sine 2 pi x?
Two pi cos 2 pi x.
Right. So what's the second derivative of sine 2 pi x?
Minus 4 pi squared sine 2 pi x.
Oh, very good. Okay, so what function, when I take its derivative twice, gives me 1?
X squared by 2.
Very good. 100. Right? Okay, very good. So we have that function that you came up with plus a constant could be a solution to the differential equation, and then maybe we'll have to see about adjusting the constant to fit the boundary values. Okay, but yeah, so we have an idea of what the solution should look like. Okay, so once again, we have n nodes. We space them out evenly. The spacing is 1 over n minus 1. The estimated values then at these nodes are u1, u2, u0, u1, u2 up to un minus 1. Now we were given the values at the boundaries, so u0 is, we specified that y of 0 equals 0, so u0 equals 0. And we specified that y of 1 is equal to 1/2, so u sub n minus 1 equals 1/2. Okay, so then you say, all right, how am I going to calculate these second derivatives at uk? Well, I'll use the central difference scheme, which is of order delta squared. Okay, I mean, you could get a scheme which was better, might be, but then you would be using 5 nodes instead of 3 nodes when you're doing the calculations. Okay. So now how do we set this up? Okay. So U0 equals 0. Then the second derivative at UI, oh, sorry, the second derivative at the node which has x value xi is approximated as ui minus 1 plus ui plus 1 minus twice ui over delta squared. That's my approximation for the second derivative at the node I, at the ith node. And the right-hand side is supposed to be this thing. It's supposed to be minus 4 pi squared sine of 2 pi x. This is when x is equal to xi, sorry, plus 1. This is when x is equal to xi. So minus 4 pi squared sine of 2 pi xi plus 1. And the value at the last node is given by the boundary condition. That's supposed to be equal to 1/2. So is that okay? All right. I mean, this is sort of the, since Python is going to be doing all the solving for you, the human part of this, the intelligent part of this, is setting up these equations. So if there's any question about where these equations came from, these equations which involve the u sub i's, then you have to let me know. Okay. But all right, let's go on until you have a question. All right. So just to see it concretely, right, in a small system where I can see everything, I'm going to I'm going to multiply through by delta squared. So then this is what the system looks like, right? I've taken the delta squared out and it's now over on the right-hand side. Okay. All right. So the first equation says 1 times u0 equals 0. The last equation says 1 times u4 equals 1/2, or 1 times u0 equals 0 and 1 times u sub n minus 1 equals 1/2. Okay. And then all the other equations are the central difference formula for the interior nodes. Okay. So I've just turned this system up here into a matrix vector AX equals B kind of linear algebra problem. Okay. So once again, I'm going to use A for the big square matrix, and then I'm going to use B for the column vector on the right-hand side.
Sir?
Yeah.
Are there supposed to be 2 more ones in this, above the first minus 2 and below the second, the third minus 2, or is it supposed to be like this?
No, I don't think so. Or should you're saying should there be a one more one in the last equation, in the last row?
Yeah, is there supposed to be one there, or
No.
is there a reason why it's not there? Since like
yeah. So this last row, all it says is that 1 times u4 is equal to 1/2. u4 equals 1/2. That's the boundary condition.
Oh yeah, okay.
Yeah. Okay. All right, now there would be different ways of doing this. One would be to do some algebra and take the boundary conditions out of things, and then you'd have a slightly smaller matrix to work with, for example. But, you know, I think just however you want to do it, you're going to end up with, whether it's this or something equivalent, you're going to end up with a tridiagonal system. Okay. So now, once again, I need numpy arrays, so import numpy module. I need to construct sparse matrices. So scipy.sparse, I need to import that module. Specify the number of nodes. Okay. Linspace, well, what's the interval? It starts at 0, it stops at 1. I want n nodes, equally spaced nodes on that interval. And I'd like to know what the internodal spacing is. So I'm going to set return step equal to true. And the default is that it's false. And that gives me my delta. Okay. All right. So the first diagonal, let's call this the diagonal. I've got a 1, a 1, a 1, all ones all the way down to the last line, last row, and I have a 0 there. Okay. And remember, it's one entry smaller than the main diagonal. So the lower diagonal, which I'm calling diagonal 1, it consists of 1s except for the last entry, which is a 0. Okay, the main diagonal, it has n entries. All of those entries are -2, except the first one and the last one are equal to 1. Okay, so diag 2 is the main diagonal. Diag 3 consists of all 1s except the first entry, which is 0. So diag 3, the upper diagonal, consists of all 1s except the first entry, which is 0. And there are n-1 entries here, instead of like the main diagonal, which is n entries. Okay, so once again, I construct these. I use the sparse module, the method diags, to construct a matrix out of diagonals. The 3 non-zero diagonals are the lower, main, and upper diagonals. So for lower diagonal, you specify an offset from the main diagonal by 1. Right? You specify for the main diagonal, your offset is 0 because the main diagonal is on the main diagonal. And for the upper diagonal, you're 1 above the main diagonal. So you specify 1 for that offset. And you give it a format, and a format that will work for the next thing that we need to do is the Csr format. Okay. For the boundary, for the right-hand side B, all the entries look like -4 pi squared delta squared sine of 2 pi xi plus delta squared. So do that. Remember that your pi there's a pi inside of numpy, and there's a sine function which operates on arrays element-wise, which also lives inside of numpy, so np.sine plus delta squared. And remember that your boundary values were specified as 0 and 0.5. Okay, so now import the module that contains the solver, spsolve. So we import that. And now we use spsolve and we give it A and B, and it will return the result of the solution for AX equals B. Now we will plot that result and we'll compare it to the exact solution, which is sine of 2 pi x plus 0.5 x squared. And if we compare the two, then we see that everything works. Okay. So once again, the reason I'm doing this is that our interest was in solving the Black-Scholes equation. What that does is it advances in time, right? It's like a nonlinear heat equation. So it's going forward in time, but at each time step, you're having to solve a boundary value problem. So I wanted to show you practically using Python how we would go about solving boundary value problems. And to once again impress upon you that when we're solving AX equals B for problems in this course, typically that A has a structure, and you want to use the method which exploits and makes use of that structure rather than doing a full matrix inverse. Okay, that's a very bad thing to do. You should think 10 times before you ever do that. Okay. All right then. Are there any questions? Okay. If there are no questions, then I'll see you next week.